Mirror equation problems can be intimidating when you first deal with them, and that's not because the mirror equation is all that difficult. It's kind of easy. It's just a few fractions added together. The place where it gets tricky is deciding whether these should be positive or negative. So there's a bunch of positive and negative sign decisions that you have to make, and if you make even one of those incorrectly, you can get the wrong answer. So let's do a few mirror equation problems, and you can see how the signs work. Now I have to warn you, everyone has their own sign convention. There's a lot of different sign conventions when you deal with optics. The one I'm going to use is the one that I feel like most textbooks are using these days, and it's the one where anything on the front side of the mirror, so by front side, your eye should be over here somewhere. So let's say your eye's over here, right? You're looking at some object, maybe it's an arrow or a crayon right here, a blue crayon. You're holding in front of this mirror right here. So this is the mirror right here. And the convention I'm using is that anything on this side of the mirror is going to be counted as positive. So if it's a focal point on that side, positive. If it's an object distance on this side, it's positive. And if the image distance comes out positive, you'll know that it's also on this front side of the mirror. Anything that comes out negative, so if we get a negative image distance after we do our calculation, we'll know that that thing is behind the mirror. That kind of makes sense. Negative like behind, positive like in front. So this side over here is in front of the mirror, positive. And back here would be behind the mirror, and that would be negative. So I've got some numbers in here already. Let's just solve this one. So what do? We're going to use this mirror equation. We're going to say that 1 over the focal length. And already we have to decide on a positive or negative sign. So this mirror, the way it's shaped right here, based on how we're looking at it, is a concave mirror. And with the sign conventions we just discussed and the signs I'm using in this formula, concave mirrors always have a positive focal length. So in other words, since this focal point is 4 centimeters from the center of the mirror, I'm going to have to plug in the focal length as positive 4 centimeters. Notice I'm not converting. That's okay. If you leave everything in centimeters, you'll just get an answer in centimeters. So it's okay. You don't have to convert as long as everything's in the same units. And we'll set that equal to 1 over the object distance. Just one other warning. Sometimes instead of DO, you'll see this as SO for object distance, or you might see DI as SI for image distance. It's the same thing. It's just a different letter. So the object distance, again, is on this side in front of the mirror. So it's going to be positive 12 centimeters since it's located 12 centimeters from the center of the mirror. So this is also going to be positive 12 centimeters. And now we're going to add to that 1 over the image distance. The image distance, we don't know. I haven't drawn the image on here. It's going to be a surprise. We don't know what this is going to be, but we can solve for it. So we can solve for image distance. I'll subtract 1 over 12 from both sides, which will give us 1 over 4 centimeters minus 1 over 12 centimeters. And that's going to have to equal 1 over the image distance. So 1/4 you could rewrite as 3/12. So 3/12 minus 1/12 is just going to be 2/12, and that's going to equal 1 over the image distance. But 2/12 is just 1/6. So 1 over the image distance is just going to be 1/6. But that's what 1 over the image distance is. Sometimes people forget to flip this at the end. We don't want 1 over the image distance. We want the image distance. So finally, you take 1 over each side, and we solve and we get that the image distance is going to be 6 centimeters. And it came out positive. That's important. This came out to be positive 6 centimeters. So where's our image going to be? So since this image distance came out to be positive, our image is going to be in front of the mirror. So it's going to be over here, and it's going to be 6 centimeters from the mirror somewhere around here. So at this point right here is where our image is going to be. But we don't know how big it's going to be or whether it's right side up or upside down. To figure that out, we have to use a different equation, and that equation is called the magnification equation. It says that the magnification is equal to the height of the image divided by the height of the object, and that's equal to negative the image distance divided by the object distance. So it turns out this ratio of negative image distance over object distance is always equal to the ratio of the height of the image over the height of the object. So what's the height of our image going to be? Let's just solve for it. If we solve for the height of our image, we get that the height of the image is going to be, multiply both sides by HO, we'll have the negative signs already here, so negative height of the object times this ratio of the image distance over the object distance. And now we can just plug in numbers. The height of the object, it says it's 3 centimeters tall right here, so it's 3 centimeters, so negative 3 centimeters, times the ratio of the image distance was 6, the object distance was 12. And so if you solve this, you'll get 1/2 of negative 3, which is negative 1.5 centimeters. The negative sign means that this image got inverted. So it got flipped over. It's going to be upside down compared to what it was before. And the 1.5 is how tall it's going to be. So what we end up with is an image 6 centimeters from the mirror, and it's going to have a height half as tall, so 1.5 centimeters, and it's going to be upside down because of this negative sign. So it's going to be 1.5 centimeters tall and upside down. That's what you're going to see if you look into this mirror. It's like a funhouse mirror. It's a weird curved mirror. You'd see an upside down image right here. It might look like you could reach out and grab it, but it's going to be an optical illusion. There's going to be no object there. It's just going to be the image of this object here. So that's an example using a concave mirror. What would change? What if we did this? What if we took our object, so say we don't put it here anymore, we move it inside here. So instead of being at 12 centimeters, we moved it to like 3 centimeters. What would we do differently? Everything would be the same. We just would plug in, instead of positive 12 down here, we'd plug in positive 3. So the mirror equation works exactly the same. You still plug in whatever that object distance is. You solve for your image distance, we're of course going to get a different image distance, but whatever you get, that would tell you where the image is, and then you would take that, plug it into the magnification equation if you wanted to decide how big the image is going to be and whether it's going to be right side up or upside down. So these numbers are going to be different, but you would use this equation the exact same way. Now what would happen if instead of using a concave mirror, we used a convex mirror? Let's say we used a mirror shaped like this. So imagine our eye again is over here looking at this object inside of the mirror, and we're going to see an image of the object. We're going to see the object right here, but we're also going to see the image of the object. And this mirror this time, instead of concave, this is a convex mirror. So its focal length is behind the mirror. So what do we do now to figure out where the image is? We again use the mirror equation. We're going to use the same equation. We're going to have 1 over the focal length, and again, I immediately have to make a decision on the sign. With the convention that I'm using, this focal length is behind the mirror, so this focal length for a convex mirror is going to be negative. So this would be negative 4 centimeters, and that's going to equal 1 over the object distance. Well, again, the object is in front of the mirror, 12 centimeters, so this object distance is going to be positive 12 centimeters. And then we add to that the image distance, which we don't know. This is what we're going to solve for. So this time if we solve, we're going to have 1 over negative 4. And again, we have to subtract 1 over 12. And that's all going to have to be equal to 1 over the image distance. So now on the left-hand side, we have negative 1/4, but that's the same as negative 3/12. So negative 3/12 minus 1/12 is the same as negative 4/12. And that's got to equal 1 over the image distance. But negative 4/12 is the same as negative 1/3. So 1 over the image distance has to be equal to negative 1/3. And if we flip that over, we get that the image distance finally is going to be negative 3 centimeters. So in other words, this here is negative 1/3. So when you flip that over, you get that the image distance is negative 3 centimeters. Where's this image going to be? Well, since it came out negative, that means it's behind the mirror, because that's the sign convention we're using. So it's going to be 3 centimeters behind the mirror. So it's going to be like over here, about at this point right around here somewhere. 3 centimeters behind this mirror. And again, if we want to figure out how tall it's going to be, whether it's right side up or upside down, we're going to have to use the magnification equation. And that magnification equation looked like this. It said that the height of the image over the height of the object had to be negative image distance over object distance. So let's just see what this right hand side is going to be. If we just set this equal to, it's going to be negative of, negative 3 is the image distance. So I have to plug in the negative 3, and you keep that negative in there. This negative out here comes along always, but now we have another negative inside of this image distance of negative 3. And the object distance again was 12 centimeters. So what are we left with? We get negative of negative 3, which is positive 3, over 12, which is positive 1/4. And the centimeters cancel. So what this ratio tells you, which is the magnification, is that the image is not going to be inverted. This positive means it's going to be right side up, and the 1/4 ratio means it's going to be 1/4 as large, the image I should say is going to be 1/4 as large as the object is going to be. And the reason is, this ratio is equal to height of the image over the height of the object. So in other words, if I want to multiply both sides, I I can say that height of the image is equal to positive 1/4 times the height of the object. Well, the height of our object was 3 centimeters in this case, but whatever your height of the object is, you multiply it by this ratio of negative di over do, and you get what the height of the image is going to be. So we're going to get 1/4 of 3, so we get positive 3/4 of a centimeter. So it's going to be tiny. This is going to be little image that's going to be right side up. So it's going to be right here, but it's going to be teeny. It's only going to be like this, 3/4 of a centimeter tall. That's what our image is going to look like. So recapping, you can use the mirror equation to figure out where the images are going to be located. The sign convention we're using is that objects, images, and focal lengths in front of the mirror are going to be positive. Anything behind the mirror is going to be negative. And you could use the magnification equation to figure out how tall the image is going to be relative to the object by taking negative the image distance over the object distance.